Lecture 20 is on gradients in curvilinear coordinates. I will try to keep this very brief. In short, we know how to calculate the gradient in Cartesian coordinates. Easy enough, right? Partial f, partial x, comma, partial f, partial y. And of course we can rewrite that as x hat partial f partial x plus y hat partial f partial y if we want to look at it like that. What you have not told you yet, but is true, is you can also write it in terms of the polar frame. You can write it as r hat partial f partial r plus 1 over r theta hat partial f partial theta. So this is the natural formula in the world of polar coordinates. Now here, I'll just remind you, r hat is, cosine theta, sine theta, you might recall that, right? And theta hat is, I think, minus sine theta, cosine theta. Right? So those are the polar coordinate frame. In fact, when it gets to n equals 3, the story continues. N equals 3, of course, when we have a function of 3 variables, though then the gradient's a little bit more exciting. We've got x, y, and z partial derivatives, right? And then we could also look at a function. If we can look at a function in terms of x, y, and z, we could convert it to a function of cylindrical coordinates, r theta and z. And so there the gradient is kind of just like what we saw before for the polar coordinates, but we have to add a partial z, partial f, partial z term. So that's not too surprising if you believe me about the polar case. And then this is where it gets weird. If you rewrote your function in terms of spherical coordinates, then the gradient in spherical coordinate picks up some of these kind of snazzy form factors, 1 over rho for the phi hat part, and 1 over rho sine phi for the theta hat part. And so in this section in my book, notes, I derive those formulas, at least in part. So so to start, what is the derivation? How do you actually show that those formulas are true? I'll try to, just briefly describe. It's essentially two things. It is remembering what the definition of r hat and theta hat is. All right. And in addition, you need to, solve that for. So I took that, said, okay, great. Well, then if that's the case, then I can solve for x hat, y hat. X hat I can write in terms of r hat and theta, and y hat I can write in terms of x hat and y hat I can both write in terms of r hat and theta hat, like so. And then if I plug that into the formula for the gradient, well, that gives me this. This is my x hat, this is my y hat. And remember, we also figured out that partial x in terms of the r and theta derivatives was this back in our chain rule section. And partial y was this in terms of the r and theta derivatives back in that chain rule section. Remember that? Okay, well, whether or not you remember it, it's still the case. It's back there, you can look. And so I can convert partial x and partial y in terms of corresponding partial differentiations of the r and theta variables. And so this first term becomes all of that. This becomes all of that. And when you multiply this stuff out, you get cosine squared plus sine squared r hat, right? You get theta hat with a minus gives me plus sine squared over r from the first term. And over here we get cosine times cosine squared over r from the second term, right? And then the cross terms cancel out. I've got like a sine cosine theta hat, but over here I've got a sine cosine theta hat. And likewise, I've got a cosine sine r hat term, and over here I've got a sine cosine r hat term, but they've got opposite signs, so they cancel out. So they're just left with these guys, which of course by the Pythagorean theorem simplifies back down to r hat partial f partial r plus theta hat 1 over r partial f partial theta. So there's the derivation at lightning speed, but there I'm sure are other ways to derive it. That's just a way. And so here's an application. If I wanted to calculate the gradient of the r cubed function, then I take the gradient of r cubed in terms of polar coordinates. That's easy. because I have r hat partial r cubed partial r plus theta hat 1 over r partial r cubed partial theta, but theta is an independent variable from r, so this is 0, and we're just left with 3 r hat r squared. You can contrast that. If you did this example in Cartesian coordinates, it would look like this. So you can take that formula, that function right there, x squared plus y squared to the 3 halves, and you can calculate the gradient of that in Cartesian coordinates. And after some suffering, you would eventually derive that it's the same as this 3r hat r squared right here. So likewise, if you wanted to look at theta, you calculate the gradient of the theta function, and it would give you 1 over r theta hat. So there's an example. Cylindrical coordinates, I don't have anything to say about the derivation of that, really. Spherical coordinates, what I want to tell you about that is the derivation is in my notes, and you know, if you want to, there it is. In gory detail, there's the derivation of the gradient in spherical coordinates. And there is doubtless a faster way to do it. My derivation's probably clumsy and could be simplified, no doubt. But there's the gradient in spherical coordinates. And here's an example. So if you wanted to calculate the gradient of the point charge, which has the voltage is 1 over rho, well, electrostatic says that electric field is minus the gradient of the voltage. So if we do that in spherical, it's really easy. So we're calculating the gradient of V, but here V is 1 over rho, right? So where'd my cover sheet go? I'll write it on my cover sheet. I'll write this example on my cover sheet. So we've got V equals to 1 over rho, right? So I'm thinking F of rho theta phi, or phi, whatever. I guess I'm supposed to put the phi first and the theta second, sorry. Anyway, that's equal to 1 over rho. So that means that partial F partial phi equals to partial F partial theta. Sorry, I'll stop being so crooked. They're equal to 0. Whereas, of course, partial F partial rho is what? Minus 1 over rho squared, right? So when I calculate the gradient of V, I just get rho hat times minus 1 over rho squared. And then plus 0 plus 0. See, because those partial derivatives are 0. And so if the electric field is minus the gradient of the voltage function, in this case that just gives us rho hat over rho squared, which is the so-called the Coulomb field. This is a vector field which points spherically outward and drops as the squared distance from the origin. That's how gravity works in a static situation, or the charge of a point charge. The electric field of a point charge is, again, it's called the Coulomb field. So anyway, then there's another example here, I suppose. I got an uglier one. F of xyz is y over x. So this one's kind of tricky. You got to change to a spherical formula first. That's tangent of theta in sphericals. And when you calculate the gradient, it's got no rho dependence, so that's 0. It's got no phi dependence, so that's 0. And you just pick up that last term. Partial theta of tangent is secant squared, so you get secant squared theta over rho sine phi theta hat. There's the gradient of that function. So that's pretty nice. I think I have a problem, maybe a problem in your homework like that. Don't forget there's these great problems at the end of the chapter, and they have, they might be useful to you. Trying to see here right quick. I may or may not have some of these gradient and non-Cartesian problems. I can't remember if I have any or not. Oh, here's one. Maybe problem 115 will give you an additional example of what we were just doing. And problem 116, I would look at problem 115 and problem 116 to better understand this lecture. All right? So, yeah. As usual, there's some challenge problems in the homework, but hey, I didn't assign them to you either, did I? So, all right. I think that'll do it. I wish you well on test 2. It will be on us before you know. I hope you will all make it to the math battle this time. You know, that's for your best interest. Pretty much, if you come and try, I will give you full credit. You know, and so anyway, that's about all I have to say for now. So thanks, guys.